Okay, let's start where we were. So we were discussing omega, Chaitin's constant. We finished by proving that omega is a compressed version of the halting problem, right? We said that n bits of omega are enough to compute 2 to the n bits of Turing's number, so that n bits of omega can decide the halting problem for all programs of length smaller than n. By the way, just a quick question regarding to that. Can you upper bound this then? The first n bits of chi. What's its Kolmogorov of complexity or algorithmic complexity?
Infinity.
Just the first n bits.
Wait, isn't anything uncomputable?
Yep. But if you just have to compute n bits for some parameter n, there might be at least, it's at least going to be smaller than n plus k of n. That for sure. Because all strings of length n, that's a string of length n, it's a finite string.
Okay. Print that number, whatever.
Yeah. This bound would be print that number. It's the bound I just erased. Can we do better?
Well, k of omega n. No. Yeah.
Omega log n.
Yeah. There you go. Now we're talking. We're starting to think the right way. It's smaller than k of omega of log n. Right? Because what we did is that, I'm going to have to use another letter, but the first m bits of omega can be used to compute the first 2 to the m plus 1 minus 1, right, roughly 2 to the m bits of chi. And so, just by setting, so in particular, I could have just said chi 2 to the m. If I can compute that many bits, I can compute that many bits of chi. And so by setting n equals 2 to the m and log n equals m, well then if I need to compute just the first n bits of chi, only log n bits of omega are enough. And log n, that's a number, or that's a bit string of length log n. So it's upper bounded by log n. Maybe plus log n if you want. That's just an error term, but by the last result that we proved, namely m bits of omega are enough to compute 2 to the m bits of chi, well then right away we can know that chi is not an incompressible number. It's highly compressible. You just need an advice of logarithmic size, logarithmically smaller. That is the advice that you need. So yes, chi, it remains a non-computable number, and one way to see it, algorithmically speaking, is that its complexity is going to grow. Like, now we're just claiming it's an upper bound, but we could look into a lower bound, and even a lower bound would be growing to infinity. So there's no finite program which can compute arbitrarily many number of bits of chi. I'm invoking this without proof, but it's related to the uncomputability of omega. That's one way to prove it. Yeah, okay, so that's just, ways of thinking. Oh yeah, we've met that number. It is uncomputable, but it's not maximally complex. In fact, it's compressible, and yeah, we saw it last time. Omega is the compressed version of chi. Now let us pursue our analysis of omega. Proposition. Omega is random. Algorithmically. By which I mean that for all n, let me write it here, it's going to be less confusing. K of omega n is larger than n plus O of 1. Last time I finished the course, I think I said K of omega n given n. Because I think I stated that last time, just before finishing. If those of you take notes. Indeed, if I wrote given n, it's a mistake. What I want to show is K of omega n is larger than n. So the first n bits of omega, that's an n bit string. And the proposition is that it's incompressible, algorithmically random. Namely that the shortest program to give the first n bits of omega is larger than n. There's no shortcut. In other words, if omega is a compressed version of the halting problem, it cannot be more compressed. How do we prove that? First, from omega star, from omega star we get omega n. Omega star n, the shortest program for that string. Omega n can be computed. Okay. Once we have omega n, the first n bits of omega, what can we do? I'm again going to use those diagrams to make my proof a bit more visual so that you understand what happens. From omega n, we can compute chi 2 to the n plus 1 minus 1. That's an n. That's the halting problem for all programs of length n bits or less. From which we can compute the following table. That's with a O of 1 advice. So there's going to be like a program of, we can transform this into that with a constant size instruction. That's what this box means. And then once I have that, I can transform it into this with a constant size instruction. What is it? This is a list of all the programs that halt. I can run them all and check what they output. And if they output a string, say a string B, then I can say, well, that means that the string B has complexity less than n, because it was produced by one of those n-bit or less program. I'm going to ignore all programs of length more than n bits, because I have an oracle for the halting problem for all programs less than n bit. I'm going to execute all those programs and see what they produce. So I can produce this list x such that k of x is smaller or equal to n. Right, let me repeat. So I have all the programs of length less or equal to n, and I know via the bits of chi which one halt, which one don't halt. Those who are promised not to halt, I don't execute them. But those who are promised to halt, I execute them and I find their output. Whatever has been outputted in those 2 to the n plus 1 minus 1 program means by definition it has been produced by a program of length less than n bit. that means its algorithmic complexity is less or equal to n bits. So by looking at the outputs of those programs, I can produce this list.
Don't you need to feed in n to some of these boxes as well?
Okay, good question. Yeah, I'm assuming here that okay, so this was perhaps a technicality, and we had this conversation last time, but
Because it needs to be self-delimiting, these first n bits of omega. But
Yeah.
then I think that means you need to put in n bar or something in front of it.
I take omega n to be really the first n bits of omega. Not with zeros, with nothing at the end. So it's an n bit string. So written this way, omega n, omega like this n, carries the information about n within its length. Right? So if I need n, I have it by saying measure the length of that
Yeah.
auxiliary information. Right? When I write it here, I'm really on the, you have to think of it as this being now on the auxiliary information tape. And you can read the length of that resource, come back, and then do whatever you want to do. So n is given implicitly in the length of omega n. Are you okay?
Yeah.
Does the auxiliary
Yeah,
tape
I
have
think so.
blanks in the setup?
Yeah.
Okay.
Yeah. Just a reminder that every time I write this, in fact, maybe because this is redundant, I'm going to allow myself to erase them. Whenever I write this, A, B, it means it's a diagram to say that K of B given A is equal to O of 1. So in this case, A is on the auxiliary information tape, or on the computing tape. And so the length of A is given, if that's what matters to compute B. Right? So because I started from the shortest program, omega star n, this one needs to be self-delimiting. And now it produces that. But now this sits on the auxiliary information tape, and now we're going to manipulate it. We manipulate it to get this. We manipulate it to get this list.
So before the whole motivation for prefix complexity was that having free delimiters, having blanks on the tape is like cheating. But having blanks on the auxiliary tape is not considered cheating?
No. Because I want to measure the minimal program in bits to produce a string, or to produce a string given some resource. If I give some resource, it needs to be written somewhere, somehow. Not in a notion of bits, but it's very convenient to write a resource with an end marker and have access to blanks for the resources. But the philosophy for measuring the bits of the program, that using blanks might be just lifting your alphabet to having a ternary alphabet, like I said.
Okay.
So the minimization procedure when we write this, this length of all programs which, given access to A, can produce B. But that A carries its length with itself, it's not a problem.
Okay.
Good, so we're here, we have this list of all strings that have complexity less or equal to n. What can we produce from that? We can produce Zn. I'm going to remind you what Zn, we've seen it last two courses ago, but we've seen it written as Zb. This time it's just Zn. Zn by definition is the minimum over all x such that k of x is larger than n. It's the Berry paradox string. It's this. It's the first string in lexicographical order. That's why I had a minimum. I can order all the strings in lexicographic order, which is not in that set. It's the first string in lexicographic order, which has complexity larger, strictly larger than n, by definition. So as I said, we met this, but written with a capital B here and a capital B here 2 courses ago. Okay, so what have I done? I've started with some program here to get some output, and I transformed the output with constant size routines to eventually get Zn, this paradoxical string that is useful to make proofs in this field. So we have a program for Zn. Maybe this, I'm going to say it. This program for Zn is of total size what's the size? Well, I need all the bits in omega n star. That's going to be the main non-trivial part of the information. What's the length of that? Well, by definition, it's k of that. So it is of total size k of omega n. That's what I need to get started and get eventually omega n produced. And from there, I have constant size routine to get this, constant size routine to get this, constant size routine to get Zn. So plus O of 1. So k of Zn is smaller or equal to k of omega n plus O of 1. But by definition, k of Zn is larger than n, right? It is, by definition, the first one in lexicographical ordering of all strings that has complexity larger than n. So, in particular, it has complexity larger than n. Therefore, I can also write that and we have what we want to show. This proof is like a cousin of the proof of the uncomputability of the algorithmic complexity function. Like, the idea here is that if omega has a compression, then I can get into trouble by finding it too short a way of producing Zn, which by definition is complex. It has complexity larger than n. It was basically the same idea that we had when we had ZB. I think I changed it was written capital B the other day. Whereas if the idea was if we can compute the complexity function, then also we can find Zn in a too short way. So, but here we sort of put the finger on the thing. It's like, well, that's one way of getting it, and we use the very fact that Zn has complexity larger than n to lower bound the complexity of omega. Questions? Now the little cousin should be easier. And you sort of realize that's why I also give you little n for the little cousin, because
I have some sort of general question, like in these prefix-free algorithms or prefix-free Turing machines, sometimes I don't know. It's not very clear to me, like when an O of 1 program exists or not. For example, like when we showed the upper bound, like for the one which was written on the board earlier, we had a plus k of n term. I guess because you cannot write the copy function in a way which is prefix free without taking that extra thing. So some of these steps, like they're of course reasonable, but like sometimes I find myself questioning myself whether there is a prefix free way to do this computation.
Good question. Once you start having things on your auxiliary tape, which is what we have at this stage of the proof, so very fast. You can say, oh, I know of a constant size, non-prefix free program which transformed that into that. Well, that's not a problem then, because making that prefix free is also going to be constant size. You could just double the bit, so it's not going to affect the constant size. It would be problematic if you really start, to give an actual, like the example of the print program was a good one where, well, now, if you do print x, that's not prefix free. Because you're starting right away from the program itself. Now what I've done here, this is prefix free. I executed to get that. So this one has the trouble of encoding an end marker for n. But once I produce that on the auxiliary tape, well, I can transform it to that. I can transform it to that with a constant size routine. Yeah, constant size prefix free routine is also going to be constant size. Thanks for the question. Okay. If there's no more questions, we're gonna keep on going. Great. And next part I think is somewhat. It's a fun part. So what have we done? We've seen that omega is compression of the halting problem. It's as compressed as it can be because it's now incompressible or algorithmically random. Now this part, we're basically going to explore what omega encodes. It encodes plenty of useful mathematical information. So I write it like this, proposition. The first bits of omega encode the truth of many mathematical facts. Namely, those that are refutable by finite means. For instance, consider the Goldbach conjecture. Okay, so I know I said something that I have not yet defined. It's going to come. I said that the first bits of omega encode the truth of many mathematical facts, namely all those that are refutable by finite means. What does it mean to be refutable by finite means? It's nicer to think with an example. So now let me tell you about the Goldbach conjecture. It states that every even number larger than 2 is the sum of 2 primes. 4 is an even number larger than 2, and 4 is equal to 2 plus 2. 6 is equal to 3 plus 3. 8 is equal to 3 plus 5. 10 is 5 plus 5. 12 is 5 plus 7. 14 is 7 plus 7. QED. We've demonstrated the conjecture. No. It's so far so good, right? And we can program it, and yeah, it seems to always be working. It's a very simple question. It has not yet been proven. It's conjectured to be true. All right. We'll come back to go-back conjecture and to finite means, but I'll give you some other mathematical problems which are encoded in the first bits of omega because they are refutable by finite means. Go-back conjecture is one of them.
What do you mean refutable?
Yeah, it's too long to sort of, I would come back to it, but it means that if you find a counterexample, it's refuted. If you've got one number that is even, that is larger than 2, I don't know, this one, right? Maybe. That's a number that is even, it's larger than 2, and suppose I've been looking at all primes smaller than it, and none of them sum to this guy. I've got a counterexample. I can publish a paper to a very good mathematical journal and say, go-back conjecture is false. That's what it means, refutable by finite means. Finite means by an algorithm that can just verify it and find a counterexample. We will write down the algorithm for go-back conjecture. Actually, let me do it now. I'm changing my order. So example, in the case of the go-back conjecture, look at that algorithm. Q, that's the name of the program. For I equals 1, 2, 3, ... check if 2I plus 2 is equal to P1 plus P2. So what am I doing here? 2I plus 2. I'm generating all the even numbers larger than 2. Right? Because I is going to be my index. It runs for 1, 2, 3, 4, 5. 2I plus 2 runs for 4, 6, 8. And all the numbers I'm interested in. I'm going to check if it's equal to P1 plus P2, where P1 and P2 are primes. Smaller than, well, obviously they need to be smaller than 2I plus 2.
Yeah.
So that gives me a bound on the primes I'm going to be looking at. I don't have to look at infinitely many primes. At each step I have to look at only finitely many primes. I can generate them via my favorite algorithm. This algorithm might be lengthy in time, to table all the primes and verify all the possible combinations of primes, but it's doable. We just brute force it. For each of those values, we can look at all the possible combinations of primes that are smaller and check if we got that. If yes, so check if this happens for some primes. If yes, go to the next I.
By the way, kind of encoding another difficult problem, which is figuring out if P1 and P2 are prime, which is also not easy in general.
Testing primality is polynomial time.
Okay, yes, polynomial time.
But I'm sure there's more efficient ways to generate the table of primes than to go randomly at each number and testing if it's prime. I might be wrong.
Yes.
Yeah, I think so.
No.
There is. You have to change the model of computation. I don't remember the name, but there is a way of enumerating the prime numbers efficiently.
Yeah, I think it can be done in polynomial time because if for a single number you can do in polynomial time, you do for all number and it's still polynomial time with AKS. That is the paper where they prove that prime is in P, I think.
Polynomial time in what? It's going to be polynomial time in the length of the number.
Yeah.
But then you have exponentially many number between 1 and that length.
Yes.
So just going through all numbers,
Then,
that method appears to be...
The best primality number that I know, the primality test that I know is Miller-Rabin, probably.
Was that the student in the 70s who came up with?
I don't know the story,
Okay.
but
A master student, I think, in the 70s came up with an idea, like, yeah, checking if a number is a prime is in polynomial time. I think that's the story.
but I guess it is still polynomial if you. There are other primality testing because Miller-Rabin is randomized as far as I know, and it may fail because there are pseudo primes and stuff. But I don't quite remember. Probably there are deterministic primality testings, and they are polynomial time, but it's like n to the 10 or.
Okay. And anyways, I'm sure you all know by now that we're not looking into the time complexity of algorithms, so we can really brute force this calculation. There are probably efficient ways to do it. That's not what we're after. We're just after a way to do it. So if we verify that this number is the sum of two primes, we go to the next I. If not, we halt. And we can say, we found a counterexample to the goal-back conjecture. That's what it means to halt. Because we found some I such that, well, some number here that is not the sum of two primes. And we halt. So Q halts if and only if goal-back conjecture is false. And Q is quite short. In terms of bits. So what can I say? Well, its halting status is encoded in the first few bits of omega. In the first bits of omega. So that's the idea of a program that is looking for a counterexample. It tries to refute it. It tries to refute goal-back conjecture. If it has found a counterexample, it halts. If it has not, if there is no counterexample, this program will look forever. If this program looks forever, it means it will never halt. It means goal-back conjecture is true. But if I ask Omega, hey, what's the status of this program? He's going to tell me either it halts or it doesn't halt. So Omega knows the truth of goal-back conjecture because it knows if program Q doesn't halt or does halt. Now I'm realizing that I have not really come back to the notion of finite means. Let me do it here. Yeah, if they are false, so they refers to the mathematical facts. You know, the mathematical facts that are refutable by finite means. Namely, if they are false, if those mathematical facts are false, an algorithm can find a counterexample in half. That's what the algorithm Q did. Okay, just before the break, maybe I should add, so that's Goldbach's conjecture is one problem that's still open and is refutable by finite means. It's not the only one. It's funny because I like to, well, AIT came up in the 70s and the 90s, so there's still plenty of papers that are going to tell you, oh, also the truth of Fermat's last theorem is encoded in the halting status of omega, which is true. Fermat's last theorem states that this equation has no integer solutions for x, y, z greater than 1 and for n greater than 3, greater or equal to 3 and greater or equal to 1. So that's Fermat's last theorem, and yeah, also it's refutable by finite means because you're going to look for a counterexample. You have to look for numbers x, y, z, and you have to look for some number n that is larger or equal to 3 that fulfills this equation. If you find it, you've refuted Fermat's last theorem, and well, you're going to write a program for it, for this exhaustive search, and this program is going to halt if and only if Fermat's conjecture is false. So yeah, similar idea. Now also the Riemann hypothesis is refutable by finite means. However, this is less trivial. This is a non-trivial result by Matyasiewicz, because the way we usually write down the Riemann zeta function, it's not clear at all. How should we, exhaustively search for a counterexample? Because it's a function defined on a complex plane. However, Matyasiewicz showed that basically you can write a program that if there is a 0 that is not aligned on the imaginary 1/2 line, well, that program will find it and will produce an output saying Riemann's conjecture is false. Here's a counterexample. So yeah, also the Riemann conjecture, the Riemann hypothesis, is encoded in the first few bits of omega.
So basically, any conjecture that involves a statement like all so-and-so have this property, where the so-and-sos are like finite or countable or something, is for sure here, because if just finding one example will immediately prove it wrong.
Yeah.
And then apparently also includes some, it doesn't have to be countable apparently, because the Riemann one isn't countable.
Yeah, but
It's a real line that you're searching.
exactly. So the Riemann hypothesis, it's a complex valued function. We know there's some zeros on the negative real axis. These are the trivial zeros. The conjecture is that all other zeros are on the imaginary line.
1/2.
1/2.
Yeah.
Real
Part 1/2.
real part equals 1/2. And yeah, a priori, how do you search for a counterexample? Because it's a complex valued function. It could be on extremely awkward complex points. But yeah, this result of Matyasiewicz shows that it's refutable by finite means, which means that if it's false, if there's a 0 that is not on the line, a program can find it. And so determining the halting status of that program via omega will determine the truth or the falsity of Riemann hypothesis. If you're curious, it's in his book, Hilbert's 10th problem. Oh, well, that's where I read about his reshuffling of the Riemann problem to make it explicit that it's refutable in finite means.
But isn't it true that any first order logic statement either that statement or its negation can be, well, proved or disproved by finite means.
Or shown independent?
What do you mean independent? Because, well, but if that statement is independent, which means undecidable, right? Or like the axioms.
Mm-hmm.
But isn't that just that? Oh no, well, okay. That's the whole point.
After the break. After the break, that's precisely what we do. We use omega to help us tell us if we have a formal axiomatic theories. We've seen them, we're gonna come back to them. And we have a statement that is a valid statement of the formal axiomatic theory. Omega can tell us if the statement is provable in the theory, namely there's a proof of that statement in the theory. If it's refutable in the theory, namely there's a proof of the negation of the statement, like there's a proof of not that statement, or if the statement is independent of the theory. Independent of the theory means, yeah, we can take it to be true, we can take it to be false, and the theory doesn't really mind. I'll give examples of statements that we know are independent of some other formal axiomatic systems that we know. Great, let's have a break, and let's reconvene at 33 past. Reminder.
Even then, like the definition of war, what counts as a war? Are two guys stabbing each other with spears? Is that a war?
A formal axiomatic theory that I shortly denote by FAT. We saw a little while ago, maybe a month ago, that by taking a bird's eye view and a computer scientist approach to what is a formal axiomatic theory, well, to be extremely formal, it needs a proof checker algorithm. And so I can come up in whichever way I want with a string of symbols, and there's an algorithm which would say, no, not a valid proof. No, not a valid proof. Yes, that's a valid proof, and it's a valid proof of that statement. So because of the proof checker algorithm, the bottom line of our analysis of how should we think of a formal axiomatic theory in mathematics, so again, Hilbert's idea of making mathematics formal, we want formal axiomatic theories, computer science comes in. Well, we can say a formal axiomatic theory is a computably enumerable set of mathematical assertions. A formal axiomatic theory is a computably enumerable set of mathematical assertions. Right? And these assertions will be the ones that are called theorems, because those that are going to be computably enumerated by the algorithm are all the mathematical assertions for which there's a proof. To remind you the idea, we were generating all strings in lexicographical ordering of increasing length, and for each string we were checking if it was a proof of something. Most of the time it's gibberish, so we go to the next string. Eventually we find a valid proof in the language. We say, wow, that's a valid proof of that assertion. Well, that assertion is a theorem, because it's a theorem for which there is it's an assertion that is true, and for which there is a proof. Why am I doing that? Probably this. Great, so that's a reminder. We finished some time ago with this. Now, let A be a formal axiomatic theory. Let S be a syntactically correct statement. of A. So S is a statement of A. Now we are we are investigating what can the first bits of omega give us. So the first bits of omega can determine whether this one's embarrassing, Will. This whether takes a H, right?
Mm-hmm.
Thank you.
Yeah. H-E.
The other weather is
Yeah,
weather.
the weather outside.
Thanks. So the first bits of omega can determine whether three cases. One, S can be proven in A. Two, S can be refuted in A. That means that there is a proof of non-S. Or third case, S is independent of A. So yeah, independent means that neither S can be proven nor not S can be proven. And typically when we want to, in some proofs of independence, the ones I know, you also show that if I add S to the axioms then, because I can enlarge my theory. Now if my theory doesn't know about either S or not S, cannot permit to logically prove neither S nor not S, I can take S to be true in my axiom. Take my formal axiomatic theory together with S. Or I could also take my formal axiomatic theory together with not S. So there's a few classic examples. I think the most iconic one is probably the Euclid's axioms. So Euclid's axioms of geometry, he comes up with 4 axioms. And there's the 5th axiom, which has always looked a bit strange, a bit different from the other 4. And for ages, people have tried to show, as part of a puzzle, maybe the 5th axiom can be derived from the first 4. And it was a millennial quest to eventually, someone has showed that the 5th axiom is independent of the first 4. So you can take it to be true, in which case we find Euclidean geometry, or you can take it to be false, in which case we find curved geometry, either hyperbolic or elliptic curved geometry. Another example is the continuum.
But in the third case, we are in the case of proposition like that one from Gödel that is unprovable, and proposition like that.
Yeah.
Okay.
Yeah.
Yeah, because it's difficult to imagine a different one, I think.
Well, the parallel axiom, the 5th axiom of Euclid is one example.
Okay.
Which is does not exactly have the same status as Gödel. It's not like, oh, it's true and unprovable. It's just choose it. You can add it, and it works, and you can add the negation. It also works to give rise to either hyperbolic or elliptic geometry. The continuum hypothesis is another one. The continuum hypothesis states that there is no set whose cardinality is strictly larger than the natural numbers and strictly less than the real numbers. This was emitted by Cantor. And in the 60s, Cohen showed that it's independent of the axioms of set theory, of ZFC. So you can take the continuum hypothesis to be true, and it doesn't change the consistency of ZFC. If ZFC without the continuum hypothesis was consistent, then also with the continuum hypothesis it is consistent. Or you can take it to be false, and it also does not change the consistency. So that's, I guess, some background on what it means to be independent of some formal axiomatic theory. Now, so I'm claiming that the first bits of omega can determine whether S can be proven, refuted, or shown to be independent of A. How? Well, here's another program. Let me call it capital Q this time, which starts with computably enumerate the theorems of A. Awkward. We computably enumerate the theorems of A. If S is enumerated, output 1. Why? Because we are corresponding to this 1 here. S can be proven in A. S is a theorem of my formal axiomatics theory A. If not S is enumerated, output 2. Because we have it proof, well, we have a proof and a theorem then of not S. And that's it. Right? What happens? Q may still not halt. If Q does not halt, it means there is no proof of S and there is no proof of not S in A. And so S is independent. If Q loops, S is independent of A. If Q halts, well then we can look at its output, either 1 or 2, and so determine if A is a theorem or not A is a theorem. Right? Look at Q. Q is a program. Note that Q embeds the knowledge, or maybe knowledge is the wrong word, but all the defining rules and grammars and symbols of A. Because it has the axioms of A, it has the rules of inference of A, it has the proof checker algorithm. The proof checker algorithm embeds all of that. Because Q is able to computably enumerate the theorems of A. Note that Q also has whatever complexity it takes to describe S. You know, maybe S is a very, very, very long strings of symbols. Well, then Q has that embedded. But Q is still a finite size program. And so omega can tell us if Q loops or not. If it does not loop, then we can call it to see if it outputs 1 or 2. Okay, so we saw that, yeah, omega can be used to establish mathematical facts like this one, but it could also be, you know, mathematical facts of the kind. Does this formal axiomatic theory admits that as a theorem, yes or no? Or is it independent? Omega can tell us about that. Questions? So this last idea that Q sort of embeds all the axioms, the rules of inference, the proof checker algorithm with an A, we're going to come back to that in what comes. Because we're about to view Chaitin's incompleteness, which, you know, we first basically overviewed the paradox between I am unprovable, the statement of Gödel, so Gödel's incompleteness. We saw that the Turing halting problem can give an incompleteness result, and I called it the incompleteness à la Turing. And I promised that we would come back to incompleteness in the idea of Chaitin. And one of the key ideas of Chaitin is that he realized, well, yeah, if formal axiomatic theory is a computably enumerable set of mathematical assertions, what's the length of that shortest program? You know, there's going to be small axiomatic theories which contain few axioms and can be recursively enumerated by a small program. But we can enlarge our axioms. We can have more elaborate logic. We can have more elaborate rules of inference, and then that will increase the size of the complexity of the formal axiomatic theory, because, as we're about to define, the complexity of a formal axiomatic theory is the size of the shortest program which computably enumerates all the theorems. I'm going ahead of me, that's my next step.
And how does this relate to the first bits of omega? Because
Oh,
the shortest program will be represented, the halting status of the shortest program will be represented in the first few bits of omega.
yeah. So depending on how complex is A and how complex is S, Q is going to have some length, which depends on S and depends on A. But if I have enough bits of omega, omega can tell me if Q loops or Q halt. If Q loops, well, I know that the statement S is independent of A. If Q halts, I can check its output, either 1 or 2.
So you need log of the length of Q, well, log of Q.
Yeah, basically, yeah.
Of omega?
Yeah, omega of, that's a good point, can determine the halting status of Q. And so whether S is independent of the formal axiomatic theory or not, and if it's not independent, then I can run Q to know if it's proven by A or if it's refuted by A. Because if I run Q and I have the promise that Q halts, well, Q has 2 outputs, 1 or 2, which tells me if S is a theorem or not S is a theorem.
Right. And if it doesn't halt, then this is back to incompleteness. This is a statement that whose proof doesn't sit within the theorem, the formal axiomatic theory.
Yeah.
It might be true, but we don't know.
Exactly. Yeah. Okay, Chaitin's incompleteness. Definition. We define the complexity K of A of a formal axiomatic theory A as the length of the shortest program which computably enumerates the theorems of A. Theorem for any formal axiomatic theory A0. There is a constant K0. Again, K0 is going to be a constant that we fixed at the end, so it's sometimes embarrassing to read the proof because we don't know what's K0. So in parentheses, I'm going to give you a hint. K0 is very, very close to K of A0, the complexity of the formal axiomatic system. So you can think of K0 as the size of the formal axiomatic theory as we go through the statement and the proof, which is roughly of size K of A0. Okay, that's in parentheses. Such that all bit strings X all strings X in 0, 1 star except a finite number of them. The mathematical assertion you write in blue to increase readability. So I'm quoting a mathematical assertion. The string X is such that K of X is larger than K0. is true, but unprovable in A0. Let me explain. So we start with for any formal axiomatic theory A0, regardless what it is. There will correspond a constant K0, which is roughly the complexity of the formal axiomatic theory A0, such that all strings, all bit strings, except a finite number of them, this is not a grammatically correct sentence.
Yeah, that was my question.
I think I'm missing a 4. Just double check.
Yes.
Yes. It's good I have space. I'm lucky.
Your proof checker has found an error.
Yeah, we have a good proof checker.
Grammar of this
I'll be back. I'll just finish where I was doing. So for all strings except a finite number of them. So there might be a few of them that for which, forget it, that doesn't hold. But for all of them, otherwise, the mathematical assertion, this is true but unprovable. What is this? The string x is such that k of x is larger than k0. It's going to be a true fact. We're first going to verify that this is a true sentence, and then we're going to verify that it's not going to be provable. For almost all x. It's not like I came up with one crazy sentence which refers to itself and asserts its own falsity. It's really like I can come up with infinitely many statements. Well, not I can come up with, that's the problem, but there is infinitely many strings for which this is a true statement, yet it's not going to be provable in the formal axiomatic theory A0. Okay, I'm willing to take questions.
Can we estimate the cardinality of the subset of strings that do not satisfy that assertion
Yeah,
directly from K0?
yeah. There's going to be at most 2 to the K0. So, for all strings except a finite number, this finite number is 2 to the K0. We're going to see why. So we can even say, oh yeah, there's a finite number of them for which it's not true. But then for all other ones, it's true.
The x that we're talking about here are statements in the axiomatic theory?
No, x are bit strings. The statements, I cannot really write the statement in the alphabet of the formal axiomatic theory because I'm leaving the formal axiomatic theory general. That's why I put quotes. But your formal axiomatic theory, whatever its language, what it has to assert is something like, yeah, the bit string, blah, 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 is such that its complexity is larger than K0. And here's a proof. Right? I'm using quotes to denote what the statement needs to assert in its own language, but I don't have access to its own language. But we can understand what it should mean. It has to mean, the string x is such that its algorithmic complexity is larger than K0.
Okay, so the formal axiomatic theory is talking in its own language about the string x
Yes.
and its Kolmogorov complexity.
Yes. If I were to ask you a proof, please find a string x, a bit string x, it can be as long as you want, and prove me that it has complexity larger than 5,000 bits. You would first come up with maybe you would use arguments from number theory or from whatever. Eventually you would submit me your proof and I'd go like, oh yeah, it's a valid proof. But if I would, speak with a true logician, he would say, no, I want it, I want Will's proof to be written in formal axiomatic language. And usually we never do it when we do proofs, even experts, even professionals in mathematics, they never really reside to the raw language of ZFC, but in principle is doable. So your proof could be amenable, with the language of empty set, successor, whatever is the alphabet of ZFC, equal signs and inclusion signs and so on. And so your statement and your proof could be put into the language of ZFC. I'm often referring to ZFC because that's the formal axiomatic system on which the mathematics that we use is based on. So it would be a statement in the language of ZFC which asserts that. Okay.
So almost all, the point here is that almost all strings will have higher complexity than the formal axiomatic system, but the formal axiomatic system has no way of proving that.
Yep.
Okay.
Yep. You got it. First, it is true that only a finite number of strings have complexity smaller or equal to K0. Right, and we know that that number is basically 2 to the K0 plus 1. Because there's only a finite number of programs small enough that could be testifying that the string has indeed complexity smaller or equal than K0. Thus, for all other strings, the assertion is true. For all other string x, the string x is such that k of x is larger than k0. And what is all other strings? Well, it's precisely all strings except a finite number. Some people will say almost all, in the case of when you say almost all and you have a discrete set, it means all except a finite number. If you have almost all and you have a continuous set, it means all except the measure zero set. That's a different story, but just to connect the nomenclature. So we've done the first thing, for almost all strings, this is true. Now we need to show that, and it also is going to be unprovable in A0. Then suppose by contradiction that there is a string whose complexity is provably greater than K0. Consider the following program. This time I called it P. Computably enumerate all the theorems of A0. I'm just going to say computably enumerate all A0 until a statement of the form the string y is such that k of y is strictly larger than k0 for some y. My sentence is not correct. Computably enumerate A0 until a statement of the form blah blah blah, I guess, is found for some y. Output y. Now, as you can imagine, it's the third time we use this argument. We're sort of we're outputting a y which should be made by a program which is too short. Okay, so I left K0 somewhat open. I just told you that K0 is closely related to the size of the complexity of the formal axiomatic system. But K0 acts as an upper bound for P. Okay, so the program P has complexity less than K0, has length less than P0. Yet it's producing a string Y, which supposedly has a complexity larger than K0. Okay, so the program P can be made of length smaller or equal to K0, where K0 satisfies K0 is greater or equal to K of A0, K0 plus C.
Can I ask a question?
Sure.
I'm again confused about the distinction between strings and statements in the formal axiomatic theory. When you say computably enumerate A0, before you were saying that A0 has some strange symbols and some grammar rules and so on, but I was not thinking of them as bit strings.
Yeah.
But now we seem to be doing that. I mean, I don't know, is the string Y supposed to be a statement in A0 or?
Okay, thanks. What is in quotation mark is going to be written in the language of A0. It's not a bit string. but it can refer to bit strings.
Yeah, okay. So Y can be encoded in the strange alphabet of A0.
Yeah. You know, if I can write down bit strings on the board and you understand, and I take for granted that a pure logician could make my proofs cleaner, and well, a pure logician can speak of bit strings. And so the formal axiomatic theory in that statement, it's written in the alphabet of A0, but this Y refers to a bit string. And this K refers to whatever we've been teaching in this course. The length of the shortest program on a fixed universal prefix Turing machine, blah, blah, blah. You know, so A needs to be interesting enough to be able to talk about those statements. Yeah, okay. Thanks. Okay. Now, that might be a tricky part, but again, look at that program. If I would tell you what's a lower bound for the size of that program, well, it needs to be able to computably enumerate A0. So it has size at least K of A0. Also, it contains as a free parameter K0. K0 is encoded in that program. Right? So it needs to contain also the algorithmic information to, it could be a program for K0. It could be a program that is able to recursively enumerate A0 together with printing K0. Okay, and some constant bit to allow for my constant size routine. But by taking K0 large enough, eventually this is satisfied. Again, we've seen that with the proof of the uncomputability of the algorithmic complexity function, because basically as I increase K0, I'm not increasing a lot the right-hand side, but I'm increasing much more the left-hand side. So there's plenty of K0s for which that does the job. And so K0 is an upper bound for the program P, and it fulfills this equality, this inequality here. Yet, P computes a string Y whose shortest program has length Y has shortest program has length greater than K0. But P is a program of length smaller or equal to K0. Contradiction. We cannot find a proof of not even a single string that has complexity larger than some threshold. And that threshold is related with the size of the formal axiomatic system. So Chaitin's take on Gödel makes it clear that even if we increase the size of our formal axiomatic theories, we're just going to increase that threshold. But as stated, the theorem will still be true. Almost all strings, except the finite number, yes, a bit more, but whatever, are going to be such that these statements are unprovable. We simply increase the threshold. Moreover, I think it's a legit assumption to say that ZFC, or current formal axiomatic theory for set theory on which we based numbers and calculus and so on, could probably fit in a 5,000-bit program. You know, one could program a proof checker algorithm for ZFC in 5,000. If it's not 5,000, it's probably 10,000, but whatever. Let's say 5,000. Well then, one can come up with strings of 6,000 bits. And most strings of 6,000 bits are going to be incompressible. Their complexity is going to be close to 6,000 bits. So way beyond 5,000 bit complexity. So all those strings of 6,000 bits that have complexity larger than 5,000 bit, they would yield a valid statement. The string blah 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 is such that its complexity is larger than 5,000. 5,000 being roughly the complexity of ZFC. And with one such string, we come up with a statement that is true, yet unprovable in ZFC. So we don't need self-recursion statements like Gödel's proof involved. You just basically need a coin, and you throw it enough often. If it's long enough with overwhelming probabilities, you will come up with a string such that its complexity is larger than the complexity of ZFC. And so there's no proof of ZFC. There's no proof of that statement in ZFC. I'll stop here, and I'll just, to wrap up with Gödel's incompleteness, there'll be a bit of a discussions, considerations of what happens. Philosophical, I guess. Are there questions?
I'm just want to say, this contradiction means that this program P will run and run and run, but never will find a Y.
Yeah.
Yeah.
So there is no such. And what did we do? We suppose that there is a string, some string. If there's one, that's provably greater than K0. This assumption falls.
Yeah, okay.
So there is no such string, because if there is one string, it acts as a stopper for my program P. If there's no string like that, no string can be of complexity provably greater than K0, well then I can still write down that program, but it will never halt.